Damn.
Hello everyone, we are the team who will think about it participating in Smart India Hackathon. And today we are going to present our idea. We have chosen the problem statement ID 1741, where we have to develop a centralized application context aware firewall for ISRO. Let me introduce you to my team. Palash, Ayush Shah, Ankesh Gupta, Mahesh Suryavanshi, Ayush Vishwakarma, and myself Aisha. Now we will proceed with a brief explanation of our product.
Our team, will think about it, and our project is called Cyber Sangrakshak. Let's start by explaining the problem statement. We aim to implement a centralized application context aware firewall. By centralized, we mean that the firewall will be managed from a single system, giving administrators complete control over network security across multiple connected devices. Our firewall is application context aware, which means that it doesn't just analyze network traffic at a superficial level, but responds based on the specific application involved. This approach allows us to make security decisions not only based on IP addresses or ports, but also based on the intent of the application, giving us greater control over the traffic. A key feature of our project is our machine learning model for anomaly detection. We have integrated a deep learning model that analyzes traffic in real time, detecting and flagging suspicious behavior. The model has an accuracy of 99% on standard datasets, ensuring quick detection and response to anomalies like attacks or unusual data transmission, and immediately alerting the administrator if something like this happens. Technically, our firewall offers cross-platform support and can be deployed on both Windows and Linux, available as a exe package for Windows and a Debian package for Linux. We also use deep packet inspection to extract key traffic features while keeping resource usage low, making it efficient for complex environments without overloading our system. Now let's get on to what we are building. Our solution includes a web-based admin dashboard for managing multiple connected devices and firewall policies, an application layer firewall that analyzes traffic and adapts security policies based on the nature of the application involved. This will be installed on each and every node. And finally, a machine learning model that detects anomalies, automatically updates policies, and sends real-time alerts to the administrators. Now let's look at our top view architecture. In our top view architecture, the firewall acts as a gateway between all the incoming and outgoing packets and the client applications. It consists of four key components that work together to secure the network. The first component is the packet capture module, which continuously monitors and captures network traffic in real life. By utilizing deep packet inspection using libraries like CodeAPI and PCAP, this module extracts key details from each packet across multiple layers of the OSI model. It captures information from the link layer like MAC addresses, the network layer, IP addresses, the transport layer, protocols like TCP, UDP, and ports, and even the application layer, specific content or a protocol such as HTTP or DNS. This level of inspection helps the firewall fully understand the nature of the traffic flowing through the network. Once this data is generated, the firewall compares it to the static and dynamic policies. The static policy consists of predefined rules, while the dynamic policy adapts to real-time traffic behavior. Based on this analysis, the firewall decides to either accept or drop each packet, ensuring that only safe traffic reaches the client applications while harmful traffic is blocked. All of these activities are logged, and these logs are periodically sent to the admin dashboard, giving administrators full visibility over network events. These logs are also fed into the machine learning model, which uses this data to continuously learn and improve anomaly detection. Over time, the model refines its understanding of normal versus abnormal traffic patterns and helps us to identify threats more accurately. When anomalies are detected, the firewall alerts the administrator and recommends policy adjustments. In this way, our firewall combines static protection with dynamic real-time adaptation to provide robust security. At last, let's look at the applications of our firewall. In terms of applications, our firewall is not limited to simple traffic filtering. It can also prevent XSS scripting attacks and SQL injection attacks and perform deep inspection to identify potential threats. These features protect the network from a variety of attacks ranging from basic web vulnerabilities to more severe threats like data exfiltration.
So I'll be talking about the technical approach of our project. Firstly, I'll give you an overview of the tech stack that we are using. So firstly, we have the web management console for which we have used Next.js. We use it to create a dynamic, highly interactive and responsive web console for administrators. This dashboard provides real-time insights into network, including packet flow, firewall rule updates, and anomaly detection statistics. Again, we use MongoDB for storing the log data, which includes the packet metadata, rules matched, and decision outcomes. Its document-based architecture allowed us to efficiently handle large volumes of unstructured log data, ensuring quick access and seamless data retrieval. And then we use AWS, which is Amazon Web Services, to manage the queuing for packet transmission and login tasks. It helps us distribute workloads, maintain fault tolerance, handle peaks in network traffic, ensuring the firewall operates smoothly under heavy load. Next is the heart of our system. Is the anomaly detection machine learning model that has been built on cutting edge techniques. We have utilized popular libraries like Keras, TensorFlow, NumPy, Pandas, all using the Python language to build a deep neural network that continuously learns from real time data. But we didn't stop at just using neural networks. To validate the performance of our neural model, we compared it against a random forest classifier, which allows us to cross validate results and fine tune hyperparameters, ensuring that the neural network is delivering the highest accuracy possible in detecting anomalous traffic. This brings us to the real time functionality and learning of the firewall, where the power of machine learning truly enhances security and is one of our peak innovations. Next, we have the firewall agent, which has been built using the C++ and Golang languages, and we have utilized the feature of PCAP for that. Now, I'll give you a small walkthrough of our product. So let's dive right into it. Initially, a packet comes, which reaches our firewall at a specific node in the network, and it undergoes packet parsing and feature extraction. This step is crucial as it breaks down the packet into its core attributes, including source and destination addresses, port numbers, protocol types, payload information, and etc. These extracted features are then used for further decision making. The extracted features are matched against the current set of firewall policies. What makes our system unique is that these policies are continuously updated in real time based on evolving network conditions and learned patterns from past traffic. Based on this policy evaluation, if the packet matches an allowed rule, it is immediately forwarded. If no match is found, it is flagged for potential malicious activity and blocked. Now, coming to one of the innovations, we have implemented real-time data logging and machine learning integration, as I said earlier. If the packet is allowed, we don't stop here. The system collects detailed logs about this packet, including which rule was applied, packet attributes, and any additional metadata before forwarding it to the application. These logs are then transmitted to our machine learning model to analyze for potential false positives. For example, a legitimate packet might get blocked due to outdated rules, or an anomalous packet might pass through undetected. This is where our machine learning model steps in to improve the accuracy of the firewall. Our anomaly detection model has been trained on industry standard datasets such as the CSIC 2010 Web Application Attack dataset and the IoT 23 dataset, allowing it to detect a wide range of known threats with a whopping 99% accuracy. The true power of our system, however, lies in its ability to learn in real time. Every new packet that passes through the firewall, whether allowed or blocked, contributes to the ongoing training of the model. This continuous learning ensures that the model adapts to the emerging threats and improves its detection capabilities with human intervention. This model identifies pattern of new threats and changes the packet behavior that might require firewall rule adjustments. When a significant anomaly or new behavior is detected, the model sends a recommendation to the center so that the center can handle the new policy update. Again, now when the machine learning model suggests a new rule, the system provides two options. One is the basic manual approval, where the admins can review the suggestions on the dashboard and decide whether to implement them, or our state-of-art innovation, which is automated policy update, where the system can be configured to automatically apply the new rules, thus enhancing security with minimal downtime. This automation capability ensures that the firewall stays ahead of new vulnerabilities and attack vectors, effectively making it a self-healing system. In case where a packet is actually blocked, the system immediately notifies the admin via the dashboard. We have built a comprehensive logging and visualization system that not only tracks blocked packets but also provides detailed performance metrics, allowing administrators to see the frequency and type of attacks being mitigated. This visibility ensures that the admin remains fully informed about the network security status and can make manual adjustments or track performance over time. So, in summary, our product is next generation and it's a context aware firewall that not only protects against known threats but also adapts in real time to evolving security challenges. Here we have an image of a desktop firewall monitoring prototype that we have made that would be installed at each node of our system, of our product. Here we have told the committee about the status of our project, and we are glad to inform that 60% of the overall prototype is ready. You can check out the GitHub repo link for seeing the prototype in action.
This slide focuses on the feasibility and viability of our project, Cyber Sangrakshak, highlighting the key challenges, risks, and strategies to overcome them. If we look at the feasibility, we'll find that our solution leverages an AI/ML and centralized management to create a smart adaptive firewall. The firewall seamlessly integrates with existing security systems and uses open source components to keep costs low. With pre-trained ML models, deployment is quick, accurate, and efficient. Additionally, centralized deployment means that no special software or support is needed on individual nodes, making the system scalable and easier to manage. We face several key challenges. Firstly, managing diverse network applications means handling different security policies, which can be complex to handle. To handle this policy complexity, we will automate policy generation based on real-time application data, ensuring adaptive security measures. Secondly, the ML model may misidentify threats without continuous updates. For keeping the ML model updated, we will continuously feed real-time logs into the model for learning, maintaining its detection accuracy. Next, transmitting sensitive logs could pose a compliance risk under regulations like GDPR, which is the General Data Protection Regulation. To address the risk of sensitive data leaks, we will encrypt log transmissions and perform regular audits to ensure compliance. Finally, deep packet inspection may cause network slowdowns affecting overall performance. To overcome this, we are going to use efficient and lightweight API agents like GoDPI and PCAP, which will help distribute processing tasks, minimizing network latency, and maintaining performance. The last part of the slide showcases some prototype images, including logs, network node status, and policies, and demonstrates the feasibility and progress of the project.
Now, let's talk about the impact and benefits that our project Cyber Sanrakshak is providing. Number one, real-time threat detection and anomaly alerts. The system identifies and alerts on potential threats as they occur using real-time analysis to spot unusual network patterns and swiftly respond to possible security issues. Number two, centralized management of firewall policies. Firewall rules are managed from a single web-based interface, making it easier to enforce consistent policies across all network nodes and reducing manual management efforts. We also provide option to make an overall global consistent policy update or customized Personal policy update. Number three, easily scalable for growing networks and endpoints. The system is designed to scale with your network, efficiently handling new devices and increase traffic without sacrificing performance or security. Number four, reduce manual configuration of policies. Automation in policy management minimizes manual setup, allowing cybersecurity teams to concentrate on strategic tasks rather than routine configuration, which is one of our many innovations of the product. Number five, enhance security via encrypted log transmission. We have been utilizing the AES encryption in CVC mode to prevent pattern vulnerabilities. And lastly, we have prevents costly breaches by early detection. Early detection of malicious traffic helps prevent expensive branches while securing logging provides essential data for audits and analysis. And this is how the model comes into picture and provides us with the best possible solution. Coming to the research work and the references that we have used, these are the few websites and research papers that we have used and we have taken our points and understandings from. So one of them being Web Application Firewall using machine learning and features engineering by Arif Shahid, one being ML assisted Web Application Firewall by Pranav Kalaria and his team, the other being anomaly detection using machine learning techniques by Sonali Wankhede, upon which we have implemented our own logic to improve our machine learning model with the best possible industry standards. And lastly, we have used design and implementation of intelligent packet filtering in IoT to improve upon our standard packet filtering processes that we have, and it has been provided by Gustavo Berton. That's all. This is our project. Thank you.